Well, good morning. Welcome to my talk. If you're interested in talking about performance of SPI devices in the Linux kernel, you are in the right place. So, quick introduction. I'm David Lechner. You might see me on the internet as DLech. If you forget how to pronounce that, you can just ask a German speaker. They can help you out. I'm an embedded software engineer at BayLibre. I've been there for about a couple years now. We love embedded systems and open source software. We work with a lot of the usual suspects you might know, and a few years or so ago, we also started a new engineering department working on GNU toolchain stuff, so we actually have people working on the other end of the spectrum from embedded systems on supercomputers, high-performance computing kind of stuff. That's pretty cool. And fun fact, I didn't actually start out as a professional Linux hacker. I started out as a hobbyist playing with Lego Mindstorms robots. So a project I started about, 12 years ago now, was EV3 Dev, which ported Debian to the Lego Mindstorms EV3, which is a programmable brick that was the Lego's third generation robotics platform. And then since then, I've also been involved in a project called PyBricks that's brought MicroPython to some of the newer Lego products. But one of my first contributions to the kernel, or in the SPI code in the kernel, was actually improving the performance of the analog digital converter on this EV3 robot. And so it's kind of been fun to come back full circle. What used to be playing for me is now my job. So what are we going to talk about? So we're going to talk about SPI offloading. What the heck is it? Why did we make that up for? And then the goal of the project I got involved on, why we need this, and the journey of how we got it upstream. And then I'll show you the result of what actually landed upstream, and then talk about some ideas of what's next, where do we go from here, how to build on what we did. So let's get into it. So first, what is SPI offloading anyway? Well, let's get nerdy and make a definition. So very broadly speaking, we can say that SPI offloading is pretty much anything you can do to make less work for the main CPU in the Linux kernel and move that work somewhere else to some kind of specialized hardware. So we would say we're offloading that work to some kind of hardware. And in addition to saying, what is it? It's always a good idea to ask, why? Why are we doing this? So why isn't what we had in the Linux kernel good enough? That the CPU just doesn't have the performance for some of the applications that we'll see that we were working with. That interrupts just can't be serviced fast enough, or even just the CPU is not fast enough to even poke the memory mapped registers to make the SPI bus operate fast enough for some of the things we're doing. So what could SPI offloading look like? That the key feature is that there's going to be some kind of way that you can record and play back a SPI message. That this lets us create the message ahead of time in the kernel when we don't have any time constraints. And then when we need to send a message, we can do it very quickly because it's already been prepared. And usually there's going to be some kind of hardware trigger to be able to play this back, like in real time in response to some kind of hardware event. So when I was researching this, I found a couple of SPI controllers that already have drivers in the kernel that can do something kind of like this. That they have these lookup tables where you can store small programs that might have some instructions like assert the chip select, read one word, deassert the chip select, and then play these back. But these are for some SPI flash controllers. But in the kernel right now, we're not really taking advantage of this. They're just using one entry in the lookup table and reprogramming it every time we need to send a message. And then another device is the one that I worked on in this project is Analog Devices, has what they call their AXI SPI engine, and this is a FPGA-based SPI controller that they made specifically for communicating with their analog, digital, and digital analog converters. And aside from specialized hardware like that, you could also use more traditional SPI controllers. Like, for example, you could use DMA to poke the memory map registers of a SPI controller. The fine print that you probably can't read is a link to a proof of concept from Martin Spurl implementing this on Raspberry Pi. This was way back like 13 years ago. But I looked at that during the upstreaming process, but I decided not to spend too much time on it because it seemed like it couldn't quite meet the requirements of our application, but it's still a useful thing that could be worth dusting off and looking at again in the future. And finally, there's a lot of SoCs these days that have different sized cores in them, and we can do the AMP asymmetric multiprocessing where you've got the big cores are running Linux, but then you've got smaller cores that you could dedicate one to controlling the SPI controller and use that for offloading the work of the SPI controllers off of the Linux processor. So now that we've set the background, let's talk about the goal of what we actually want to set out to accomplish. And so that is analog devices. They've had their Axie SPI engine that they've been using out of tree for quite some time. And of course, like any good open source citizen ought to, we want to upstream that. And more specifically, we want to use this controller with the analog digital and digital analog converters in order to get millions of samples per second while having accurate enough timing that we can pass harmonic distortion tests and noise tests on these analog digital converters. So if we can pass those tests, then we've accomplished our goal. So we cleaned up the out-of-tree stuff, sent it upstream, and the response was, yeah, if it was that easy, I wouldn't be standing up here talking about it today. So here's the very abbreviated journey, upstreaming journey that actually took me like about a whole year, 6 revisions or so of patches to get this upstream. But so the actual feedback, first feedback was, like anytime you have a complex project like this, it's always a good idea to break it down into smaller parts and also research past efforts on the same subject. So the initial feedback from Mark Brown, the SPI maintainer, was that this was doing too much all at once and he wanted it to be more integrated into the SPI core code. And so he suggested first some more general optimizations with pre-cooking messages and then moving on to the more offload specific parts of triggering SPI messages using hardware. And he pointed out to some past conversations on the mailing list on the subject that I managed to dig up. One was from a bit more recently from David Yander talking about some general SPI performance improvements in the kernel. And then the other one was the one I mentioned already from Martin Spurl from 13, 14 years ago, talking about this idea of pre-cooking or pre-optimizing SPI messages, as well as that Raspberry Pi DMA proof of concept. And so I managed to revive the upstream work that Martin had started and got these SPI optimization stuff moved upstreamed and then moved on to the more specialized hardware offloading bits. And since this is new hardware, of course, we had to deal with the device tree bindings. So at first I was kind of like this, that I was trying way too hard. I had been studying this for many months and was looking at all the possibilities and going, there's no way we can make something that's going to work for everybody. And the SPI maintainers were like, you're overthinking this. It's really not that hard. So Rob Herring made a few simple suggestions that will look very obvious when I go to the next slide. And but I also want to give a special shout out to Connor Dooley. We had a nice lengthy conversation of like all the possibilities of how we could do SPI offloading, and what that might need to look like in device trees. And so I'm feeling much wiser about device trees now than I was before this. So, in the end, as the monitor goes, the device tree is just describing how things are wired up. So if you draw it out like this, then it's going to be pretty obvious that how you should make the bindings look. So one of the things that came out of this is that we took the trigger source provider and consumer that you might have seen in the LED subsystem and made it more generic. So in the DT schema repository now, there's the trigger sources and number trigger source cells binding that's just made generic that you can use it anywhere. So we ended up, this is showing all the different ways that the ADCs we were working with could possibly be wired up. And so we're using the, does this one work? No laser pointer, but, I got a mouse pointer. So we've had some that we've got the analog digital converter might be self-clocked, and every time a sample is ready, it's sending a signal to our SPI offload trigger to say we want to read data over the bus, but some other ones are don't have a clock, and so we need some other kind of clock source to tell us we want 1 million samples per second. So we used a PWM to give a 1 megahertz signal, and some are kind of a hybrid of both, that the PWM is telling the analog digital converter, start a conversion, then when that conversion's ready to be read back, it's sending us a signal to trigger our SPI offload, and then communicate over the bus. And then the other part of this is once the data comes back in, Linux is too busy to read it, so we're actually putting it to DMA, a DMA buffer for this IIO buffer. So for that, we ended up just using the existing DMA channel bindings for that. So there was a whole lot more on the journey, but I don't have time to talk about all of that, so we'll just jump right ahead to the results of how this ended up. So, woohoo, this landed in the 6.15 kernel, so it's available for everybody to use, try out now. And so we've got some new SPI core APIs to make use of. Earlier we talked about this idea of pre-cooking messages or pre-optimizing messages, and this has actually been in the kernel since 6.9, I believe. And this can be used with any SPI message that gets repeated multiple times and in a case where you care about performance. So like in the analog digital converters, when we're doing these buffered reads, even for the typical case that's already in the kernel, you're repeating that same SPI message over and over and over to read a sample. And there's actually, it turns out, a lot of overhead in in that processing. In particular, there's a double underscore SPI validate function that's checking all of the parameters of the SPI message and SPI transferred and filling in default values and making sure none of the things that you asked for conflict. And so this SPI optimized message will just do that once for a message, and then you can use that message over and over without having to revalidate every time. And performance measurements show that actually saves quite a bit of CPU. And so there's really no reason to not use this today already, and it works with any SPI controller, but it could also be expanded in the future for controller-specific things. There's a callback we added that if you had a callback that could do even more ahead of time, the controller driver could hook into that and add some additional optimizations, and there's potential for other additional optimizations of, maybe we could do DMA and mapping ahead of time instead of remapping every time too. That we didn't get to that yet. And then moving on to the offloading stuff that's not quite so generic. You need specialized hardware for this. But we organize these into your typical consumer provider things in the header files. So you can find those there. For the provider APIs, if you've got a SPI controller with offload capabilities, then it's going to be an offload provider. A single controller could have more than one offload instance. For example, the lookup tables that I mentioned earlier, each entry in the lookup table would be what I would call one SPI offload instance. And so a provider is going to register one offload for as many instances it can provide. Maybe it's a lot, maybe it's just one. And then it has to implement that SPI optimized message callback to be able to handle a SPI message that has the SPI message.offload field set, and that will let the SPI core code know that this is a special, or this SPI message needs to use those special offload capabilities, and then the SPI controller will look at that and see if it can handle it or not. And then separate from the offload provider, we also have trigger providers. And the trigger provider is not going to be the SPI controller itself. It's going to be the PWM or the analog digital converter. But those also have callbacks they're going to need to do to register the trigger with the kernel. And I haven't listed all of the things it needs to do, but it's got an operation table you need to fill out. The main one is a match function that you need to fill out to be able to match the provider to the consumer, whether you're using device tree bindings or whatever. And then another interesting one is there's a validate callback that works kind of like the clock round rate function, if you're familiar with that it's basically saying that if we were to set the clock to this number of hertz, what would the clock hardware actually do? Because usually the clock hardware has dividers that can't do literally any speed, and so it would feedback that what you would actually get. So we can do the same thing that lets us fail early if we need to. If we want to set the PWN to 1 million, can we actually do it exactly 1 million samples per second, or are we going to get some other number to make sure we aren't exceeding the capabilities of our ADC. Then on the consumer side, this will be your SPI peripheral, like the analog digital converter. It's got some APIs that it needs to use to ask the SPI code for, we need to get one offload instance that's going to be assigned to this analog digital converter that we can use. And then we also need to get our trigger if there's going to be a hardware trigger involved. And right now we just have support for periodic triggers, so that could be a clock, PWM, something like that. And then we also have the data ready trigger that was the one we saw on the ADC that says there's data ready to read. But we can add more to that in the future if we need to. And then right now there's only one data stream type supported, which is to DMA, that whenever we're reading so fast we're streaming our data somewhere. But in the future, if you want to stream it directly to a DSP or somewhere else, we could add more streaming syncs. But DMA is the one we've got right now. And then once you've got all the resources that you need to do the actual SPI transfer, we need to call that SPI optimize message function again, but this time we're setting the offload with the offload instance that we got to let the SPI controller know that this message is going to use those special offload capabilities. And then the struct SPI transfer has a new offload flags field that is going to let us do extra things that only an offload could do. For example, it's going to tell it to stream the data where it needs to go instead of using the usual transmitter receive buffer that goes with a SPI message. So using all that, we were able to use that with the analog digital converter drivers. We've got 5 of those upstream already that are using this offload support, and also 1 digital analog converter driver, so you can use those as a reference if you want to do something similar in another driver. And this is letting us go from our previous limit of maybe 10 or 20,000 samples per second with not very accurate timing between samples to a very precise 1 million samples per second, which is the rated maximum speed of these chips that we were working at. So to test it out, we used the IIO oscilloscope program. That's part of the libIIO stack of software. That's all free open source software that just to do kind of a quick smoke check, we punch in that we want sample rate to be 1 megahertz, so we're getting our 1 million samples per second, and we generated a 1 kilohertz sine wave, and then we used this to capture 4,000 samples. So if you do the quick math at those, we should get 4 periods of the sine wave because it's 4,000 samples of a 1 kilohertz sine wave at 1 megahertz. And so that looks good so far, but it's also always good to dig a little deeper. And we also use a digital logic probe to look at the actual SPI signals to make sure we're getting the timing that we need, because a lot of these analog digital converters have precise timings that they need, like you need a quiet time before you trigger a conversion so that things can settle and you get your accurate measurements to meet those noise and harmonic distortion tests that I mentioned earlier. So here we're looking at, you can see we've got the chip select line is running at 1 megahertz, so the chip select in this case is triggering the conversion of the analog digital converter to take 1 set of samples. And this is a simultaneous sampling, so we're actually reading 4 different things all at the same time. It's like 4 analog digital converters in one, and then the SPI bus clock is running at 80 megahertz, so that's fast enough that we can read 4 16-bit samples in that 1 microsecond time period that we have to read them, and still have a little bit of time to spare for the quiet time needed before our next sample. So we accomplished our goal of using the analog digital analog converters, but of course this is meant to be a more general framework for other applications as well. So what else could we do with it? During the reviews and discussion, here are some of the other things that got thrown around. The one that came up the most, pretty much in every discussion, was CAN controllers, that frequently Linux just can't respond fast enough to incoming messages. So some of the messages end up being dropped. But with SPI offloading, that we could quickly read those messages over the SPI bus, put them in some kind of buffer so that Linux could look at them later, and then we wouldn't be dropping those messages since the CAN controller chip would be being serviced fast enough now. And I also mentioned earlier the couple of SPI flash memory controllers that have those lookup tables, that we're not making full use of those lookup tables, so there's potential that we could do something with that in the future. And in Mark Brown's feedback, he threw out just some very broad ideas of different things we could do. Again, this all comes down to that idea of it's a message that you're repeating over and over in a use case where you care about performance. So some of the ideas he had was something as simple as reading an interrupt status register whenever you receive an interrupt over a chip, or it could be something bigger, like maybe you have a chip that needs a firmware loaded every time it comes out of sleep mode. Then we could just trigger the offload to load that firmware without Linux having to do anything. And so you would be able to come out of sleep mode much faster. Another thing that is not really related to SPI specifically, but we made the trigger source bindings generic in the device tree, but I would also like to take that one step further and make a trigger subsystem, I guess, in the Linux kernel, so that we have generic APIs that right now we just have the SPI offload trigger get, but really there's no difference between the SPI offload, the ADC telling us to trigger that versus the PWM telling the ADC to trigger a thing. So it'd be nice to use those same APIs to just get a generic trigger. Right now we're using the PWM's bindings for the ADC, but there's really no reason it has to be a PWM. It could be a clock or it could be anything else, chained from another ADC. So it'd be nice to be able to just use that more generic trigger binding. And one last thing that's on my radar, that we're talking about how to get more bits per second over a SPI bus. This isn't exactly related to offloading either, but if you're looking at this picture and you've seen a quad SPI before, you might think this is like a normal quad SPI, but no, it's not. So this is actually what we call a single SPI controller with multiple SPI buses. So in typical quad SPI, if you've got 4 serial lines, you'd be reading 4 bits of one word all at the same time. But this is different because this is more like, this is the case of the analog digital converter with 4 different analog digital converters in it that are all converting at the same time. So it's more like having 4 analog digital converter chips in parallel that are all sharing the same chip select and clock select line, but the data lines each have a separate data word from a separate analog digital converter over it. So we're reading 1 bit from 4 different words all at the same time. So that's another thing that hopefully we'll be working on upstream soon. And that's all I have for today. So thanks for listening, and we'll open it up for questions.
Yeah, you mentioned that there had to be a quiet time with some of these analog devices, to ensure that the signaling's all good. What did you have to do to ensure that you would have such a quiet time?
Yeah, so the quiet time is typically on the order of tens of nanoseconds.
Oh, okay.
But in the SPI transfer, struct SPI transfer, there's several different delays that you can put into that. Specifying that you can specify a delay after all of the data lines. You can specify a delay after the chip select, and it depends on the ADC where that delay needs to be, but there was already existing APIs in the kernel that we could put those delays where we needed them to be. And the SPI controller we're using knows how to understand that and make sure that we get at least that amount of time.
Thanks.
You mentioned that you felt much better about device trees now than you did before.
Yeah.
And I was curious, what were some things that you might have used to kind of help you get through that initial layer of confusion when you were building out your DTS?
Yeah, I guess for me it was like trying to over-design what I was doing, to try to think of everything that could possibly ever happen. But like I said, the really key for me is just remind yourself over and over that device tree is really about how things are wired up. And so if you just look at how things are interconnected, all you need is like the provider, consumer, in most cases, that's gonna be the right way to go.
To piggyback, that's a lot louder than I thought, but to piggyback off of his question, so was your primary source of like learning about device trees like other people, or did you have to take like documentation from the official, like the official kernel documentation, or a little bit of both? because I'm kind of in a bit of the same boat. Sometimes I overthink things whenever I'm doing my device trees, like for FPGAs and things like that, or like doing like some modifications for that. So I'm just curious, like, what is your sort of design workflow, however you call it?
Yeah, FPGAs are really tricky because they kind of blur the lines of what hardware can do that it's not quite wiring. But I mean, for me, it's just been experience of upstreaming lots of ADCs, and also I'm a reviewer in the IIO subsystem now, so I'm also looking at what lots of other people are doing. And so for me, that's been how I've learned, is just through experience of seeing how other people are doing it, seeing what reviews come in for them, and then you just kind of start seeing the patterns of this is the right way to do it.
So is it like you just kind of, I guess, kind of follow through other people's footsteps and do a little bit of like reading a bit of the, because there's because sometimes I use like device tree bindings docs. There's like documentation on like bindings and stuff, and sometimes the documentation can be clear and sometimes it cannot, to say the least. So I guess just follow what other people do, like see, other device tree sources that are out there, and see, just get like a good feel of like, what to do.
Yeah. Looking at similar devices is always the best thing to do, because we always want to try to reuse the same properties for the same thing, so that we're not reinventing new things every time. Like, even if it's a custom property for just one chip, a lot of times there'll be another chip that does pretty much exactly the same thing, so we want to use that same even custom property in the same way everywhere.
Thank you.
Hey, real quick on the host side, since I'm unfamiliar with the AXI, ADI, SPI controller, was that in a device or was that an FPGA that was connected to some other host device? What was your host configuration, I guess?
Yeah, so we primarily used a Z board that has an AMD FPGA in it, but we've also run it on a DE10 Nano that's got an Intel FPGA on it. But that SPI controller is free open source software. I think it's GPL2 license from ADI to use for whatever you want on GitHub.
Yeah, thanks.
Yeah, you bet.
Making me move.
So do you see that you see this could be more of a generic controller to data dump type of thing, so you could do different, not just SPI, so moving data from any other sort of source that you'd be
Yeah,
grabbing?
you could use the same principles for any other kind of communication bus, but this of course has to be specific to the SPI framework and the kernel, but all right, looks like it. So thanks very much.